Well, good afternoon, everybody, and welcome along to DBA Fundamentals Down Under for the month of November. This month, we've got Sunil Agarwal from Microsoft talking to us about strategies to get maximum concurrency for your workload in SQL Server. Now, I'll hand over to Sunil very shortly, but before I do have some housekeeping to run through. So, for those of you who aren't aware, I need to make a big call out to our sponsor, SentryOne. Without SentryOne assisting us, we wouldn't be putting on this session and you wouldn't be here today listening to Sunil. If you haven't already gone to SentryOne's website, make sure that you do have a look at their articles, videos, and downloads that are available to assist you with your learning in the SQL Server environment. Just to remind you, this session is being recorded and will be made available on the DBA Fundamentals archive site, probably within the next couple of days after this session finishes. So feel free to come back and rewatch this video. I'm sure that you'll pick up things on rewatching that you won't pick up first time around. Just a call out to you to make sure that you stay involved with PASS. We just recently had the PASS Summit in Seattle. Apart from PASS Summit, there are the local chapters, virtual chapters, like this one, that you're able to register and come along and enhance your SQL Server learning. So with that, I'll hand over to Sunil to take us through this month's session.
Hello, Warwick, can you hear me?
We can.
Okay. Warwick, thank you so much for organizing, and everybody on the call, thank you for joining. And I want to recognize SentryOne. SentryOne is a close partner of Microsoft. We work with them. They have pretty good set of tools to help you troubleshoot, monitor troubleshoot performance. So do go to their website. So with that, I want to start my session on maximizing concurrency or strategies for maximum concurrency in your SQL workload. You know, concurrency is a complex topic, often misunderstood. And I was gonna request if some of you can type in your questions, like what kind of concurrency issues you have seen, just to give me an idea where to emphasize. So I'm gonna pause for 30 seconds, and if you can just type in some questions, and then I'll be happy to proceed with the presentation. So Warwick, I'm not, let me see if there is chat.
It looks like everybody's shy. Oh, we've got one.
Okay.
But they're just learning. They haven't got anything for us at this stage. Okay. Everybody, feel free to ask questions in the questions tab. I will be monitoring those, and we'll let Sunil know of your questions throughout the session.
Got it. So let's start. So a bit about myself. I've been with databases for a long time. I've been with databases for 34 years. I can't believe myself. And I've been with SQL Server team for 15 years. Before that, I worked for Sybase. I worked for a few startups developing applications. And I also worked for a company that some of you may remember, a Digital Equipment Corporation, a phenomenal company. It is no longer in business today. And that's the lesson to be learned about technology. Technology changes so frequently or so quickly, one has to keep up. Anyway, so that is about my background. And so concurrency, as I was explaining, is often misunderstood. It's a complex topic. And so what I was going to do, I'm going to just start from the basics. And along those basics, I will describe to you some blocking that happens and how can you remove those blocking and so on. So my expectation after this presentation is done that you have a general idea about locking, blocking, latching, and some idea on what to do to get rid of it. I don't expect anybody to become an expert in concurrency. This is a long haul. It takes time, needs a lot more experience. And so, but I think with the basic that I'm going to describe, you should be able to move forward. I have also done a lot of blogging on concurrency. If you search snapshot isolation or concurrency under my name, Sunil Agarwal, you will find those blogs. And if you don't, send me mail. I will send you the link. Okay. All right. So what I was gonna describe to you, concurrency models. What are those? And there is also a talk on locking, granularity, and lock escalation, latching, snapshot isolations, and deadlocks. So this is the topics, and that I'm going to walk through. I don't expect to finish all of them in 1 hour, but I think I'm going to just start from the most useful first, so that you get something out of this presentation. Now, I also realize, like some of you may be debugging concurrency issues in a complex application environment, and that kind of complexity is not going to be reflected in my presentation. It is mostly on fundamentals, and as you know, solving those complex concurrency problems is time-consuming. But I'm going to showcase certain things, especially in 2017, and new management studio that makes it a little bit easier. All right? Okay. So now,
sorry, Sunil, would you be able to just try dropping out of presentation mode and back in again? The GoToWebinar is just blocking part of the screen, that's all.
Oh, it is? Okay. So I go back to what again?
If you refire that up.
Okay.
Hopefully, it's staying in front.
What does that mean?
If it's just blocking a little bit on the very left-hand side of the screen, that's all. But we should still be good.
Okay, let me do one thing. Let's see this. How's that? Okay. Same thing.
It's moved it over to the right-hand side, but that should be better than on the left-hand side and not covering any of the points.
Okay. All right.
Thank you.
Yeah, sure. So the concurrency basically means how do we allow multiple users, whether it is an application or whatever, at the same time in the database, and that must, like that multiple users accessing database must see some sort of a coherent or consistent view of the data, right? What it means is, let's say I as a user, I'm modifying some table, right? Now I do that modification in a context of a transaction, right? Transaction is a very fundamental construct in a database. So you start a transaction, you make a modification, and if you're happy with the modification, you commit the transaction. So the point is, while I made the modification, nobody should see the data, right? Because I may change my mind, I may roll back the transaction, right? Like, for example, you go to a bank, you want to deposit some money into your account, you are typing the amount you want to deposit, and then you realize you typed the wrong amount, right? You can abort the transaction, right? So nobody should see your account to say, yeah, Sunil has this much money in the account, because I have not yet committed my transaction, right? However, when I commit my transaction, then everybody who has the permission to see my account should be able to see that, right? So there is a state of the database during a transaction while it is not committed, and there's a state after the transaction is committed. Okay, this is actually an important one. And I think the isolation level. So, and I'm going to explain to you isolation level in that context. So this isolation level that I'm describing here, it is not something that Microsoft created. This is not Microsoft. This is a standard SQL, ANSI SQL committee that defined the language of how to query SQL Server, how to query a database, and what kind of concurrency we allow, right? So this isolation levels, as the name implies, it means isolation from concurrent activities, right? That's what isolation level means. Now, at the most unmanaged or most relaxed isolation level is called read uncommitted. So what it means is that if I want to query a table under a isolation level called read uncommitted, as you can guess, the name says read uncommitted data. That means I'm allowed to see uncommitted data. So for example that I was giving about the bank account, I went and I start my deposit, I typed the wrong number. If somebody else, like a bank officer, was running a query about my balance under read uncommitted, that officer will see the transient data that is not yet committed, right? So that is the least secure or least consistent isolation level, right? Now the beauty of this isolation level is that you are not blocked, right? Because if I'm querying under read uncommitted, if I was inserting row into my account, you can see my data, you're not going to be blocked, right? So where this isolation level is important. Now think about statistical data. Suppose I'm trying to run some query which tells me statistically, show me the let's say the salary of, or like average salary of people in Australia. Let's say that, right? Now clearly when I'm running the query, salaries may get modified along the way, but I'm not interested in finding exact salaries. I'm just looking at the average. So it may be okay for me to run that query in a read uncommitted motion, right? So that will be one example. The most common way we access data inside SQL Server is under read committed. In fact, this is the default isolation level, right? Default isolation level. What it means is that I will, if I query a table, I will only see the data that is committed, right? I will not see a uncommitted data, right? So that means the bank example I was giving, if I do this query, which is a default isolation level, it will block because I was making a deposit and somebody wants to query it. Until the deposit is complete, they will get blocked, right? So that is the normal behavior. This is where you will find that a lot of applications see blocking. And this is actually especially interesting because like some applications that migrate from, say, Oracle read committed is not blocking. Okay, in Microsoft SQL Server, read committed is blocking. So sometimes when you migrate your application from Oracle to SQL, you will see a lot more blocking, and people say, well, SQL Server isolation level or concurrency is not as good. Now, interestingly, I'm going to talk about that. Starting with 2005, that is 12 years ago, we created a mode for read committed that is non-blocking, and this is what we recommend to most customers. Okay, so that is something to keep in mind. In fact, if I'm not wrong, SQL DB, like our Azure database, runs with that mode by default. Okay, that means non-blocking read committed. Let's table that point, but for now, on this slide, read committed guarantees that you can only read the data that is committed. If the data is being changed, you will block. And once the change has committed, you will see the data, right? So that is read committed. Now, interesting thing about read committed is if I run the same query again, I may see different row, because next time when I ran, somebody else might have committed the transaction, another transaction that changed the value, right? So read committed means every time I run, I can potentially, not necessarily, I can potentially see different values, right? I hope that is clear. The next isolation level is repeatable read, right? This is more, as we go down in this list, this is more strict isolation level. Repeatable read means if I read something in my transaction, right, as a begin transaction, read Sunil's salary, that's that, and now if I want to read that thing again, I should be guaranteed that whatever I read before is still true. And SQL Server implements this isolation level, actually all isolation levels, using a lock. So in the read committed scenario, when you say read, say Sunil's balance or salary, it takes a read lock, and once it reads the value, it releases the read lock. It does not hold it. That means somebody else can come and modify that data. In repeatable read mode, if I'm reading it, I'm going to take a lock for the duration of my transaction. That means if I read the query again in my transaction, it will be still the same. That means anybody who wants to change that value will block, because I'm holding a share lock. So that is a repeatable lock. So what you see here is that the higher the consistency or the guarantee, the more locking and blocking that you will see. You see that point? It's an important point. Like read uncommitted, minimal amount of blocking. Read committed, some more. Repeatable read, lot more, right? And then repeatable read, here's the point. If I say I want to, I'll give you a different example about repeatable read. Let's say I want to find out the average age of the people who are attending this conference call, right? Okay. So I run the query. I said begin transaction, find me the average age of the people attending this conference, this talk. Now I made sure I took a lock on each of those people, right? That's a repeatable read, because if I run the same query again, I will make sure there's nothing changing for the guys I read about, right? Now imagine this. Now somebody else joins the call. Like now somebody joins the call, and I run my query again. Show me the average age of the attendees for this call. That will change because I did not hold a read lock on something that did not exist like a minute ago, right? Because this is a new row. So repeatable read does not prevent from phantoms. Phantoms means the new row can come, and because those rows were not there before, I will see them when I run the query again. Now, if you want to avoid those phantoms, you take a serializable isolation level, right? Serializable isolation level will say, I will make sure that data never changes for the query for entirety. Even the new data that is not yet in the system, I'll make sure that data does not enter into the system so that you in the query see the consistent view, right? So these are the 4 isolation levels. Now, SQL Server has implemented these isolation levels using locking, and we call it pessimistic locking. And now this is a confusing word, but I think I'll tell you what pessimistic locking means to me. Now imagine this, right? You come to office, for example, one day very early in the morning. Let's say nobody was in the office. You run a query on your database as a select something, where something, right? SQL Server will take a lock on the rows that you're reading, right? Whether it's read committed or repeatable read, take a lock. There is no way to tell SQL Server, guys, SQL Server, this is morning, there's nobody accessing the data. Don't take a lock because I'm the only person in the system today, right? But the SQL Server will take the lock. So that is pessimistic. It assumes that somebody will do a modification, so it wants to guard it. That's a pessimistic locking. Okay, optimistic locking means I will only take the lock when there is a need. Otherwise, if there's nobody in the system, I will not take a lock. And we have a new execution mode or new memory optimized tables that was introduced in 2014. That actually is the optimistic locking. Okay, so we will touch upon that point in one of these slides. Okay, so now the locks are row locks, page locks, table locks. You have seen those things, right? Now let me show you a quick demo on these isolation levels. Okay, all right, we finished 20 minutes already, so let's just work through these things in the demo. Okay, so here what I'm going to show you, I have a table, lock test table, and let me just make sure I'm in that database. Sorry, I have a lock test database. I said the table, I'm sorry, and I have a table which I call lock test basic locking. So I'm going to drop that table, right? Then I'm going to create this table. I created this table, and now what I'm going to do is I'm going to insert 5,000 rows into this table. So table got like 5,000 rows, and if I do a count star on this table, 5,000 tables, right? No problem. Now what I want to show you is the locks taken for each isolation level. All right. So here is a query that I use to show you the locks. This is one of my favorite way to look at the locks. If I look at the locks right now, okay, I'm just going to look at the locks. And don't worry about this query. I'm going to send you, Warwick, is there a way to upload these session demos? I'll do that so that everybody can access it, okay? So let me just do
Sure. At the end of the session, just send them through to me, and we'll be able to have them placed onto the archive website along with the recording.
Sounds good. So let me run this query. So notice something. There is a lock on the database ID 7. You see that share lock? This is the share lock. And there are 3 sessions, 51, 52, and 53, because these are 3 sessions here, right? Okay. Now, why there is a share lock on the database? The point is, these sessions are using the database, right? So that's a share lock. That means nobody can come and drop the database, right? So this is how we are protecting the sanity of a database for sessions that are active in a database, all right? So that is the query I'll be using to figure out the locks. Okay. Now, if I do a begin transaction, so I'm going to begin a transaction, okay? And now I'm going to say select star from this table, which is 5,000 rows, right? And I'm saying use read committed. Even if I did not say read committed, by default it will be read committed. Okay. So if I run this command, I'll see 5,000 rows. And notice the transaction has not yet committed, right? I did not say commit. If I go back and look at the logs, you don't see any logs. So what happened behind the scene, I could show you through X event, but I'm not gonna do that to save the time. So in the background, what happened, SQL Server went ahead and logged each row separately, read the row, release the log, next row, release the log, and so on. They required 5,000 logs and released 5,000 logs, okay, behind the scene. Nothing is left, right? So this is the read committed. Now let me go and now do the repeatable read. Okay, I just said C1 less than 100 because I want to show you the output. Now here is the deal. When I'm saying select star from my basic locking table under repeatable read, so the deal is once I read a row, I'm going to hold the log for the duration of the transaction. So let me run this guy. Okay, and okay, so it did that, right? So now if I go and look at the logs, okay, I look at the logs, and what I want to show you is something happened here. Okay, I want to show you the logs on the first I want to show you the log at the object level. So notice I have a intent share log on the table, What does intent share lock means? Intent lock means that somebody has a share lock on one or more rows or page in the table. What it means is that if I want to come and want to drop this table in a separate session, if SQL Server has a intent lock on that table, that means the blocker, dropping the table cannot be allowed, because this is a very quick way to know that somebody holds a lock. And I want to emphasize this point more. Imagine if you had a table with, say, 1 million rows, a lot of rows, and let's say I have a share lock on one row. Now you want to drop that table. Now, before you can drop, SQL Server has to check if anybody has a share lock on anything in the table. Now, if there was no intent lock, SQL Server has to figure out which row was locked, right? It has to walk through that tree. Intent lock is a very easy way to figure out what's happening at the object level. Okay, that is about the intent. Now, what I'm going to do, I'm going to change this query. That's why I have all these comments. I'm going to comment this out, and I'm going to run this query. I want to see the red. The reason I'm going to do red is because that's the lock I'm taking on the row ID, each row that I locked. So remember, my query was where C1 is less than 100. In fact, when I inserted the rows for this query, I should see 100 rows. All right. So if I look at the bottom in my lock, you will notice that I have 100 rows that are locked. These are 100 rows, right? You see that? And the reason I'm holding the lock, because I'm running this thing under repeatable wait. Make sense? Okay. So this is important. Now I'm going to do the same query, and I'm going to run under serializable. Okay, serializable. Now in this case, if I go and run my query here to see what locking happened, and I'm going to run at the object level. I'm going to take this guy out. So notice now the lock I got is a share lock. It is not the intent lock, the share lock. The point is, if I have a share lock on the table, that means nobody can insert a row into this table. You agree? Nobody can insert the row. And the reason I'm trying to do that is because my query was select star from basic locking. I'm selecting all the rows. If I did not take a share lock on the table, somebody inserts a row, I will not be protected, right? That's why I'm taking a share lock. Now you can ask, well, this is too much, taking a share lock on the table. This is like loading the whole, stopping everybody. Now, in this case, because there is no index, so if you want to run a query, for example, if I'm running a query like this one, where, I'm going to type it here, where C1 is less than 100, right? If I run this query, so what happens is, if you had a cluster index on C1, assuming you had a cluster index on C1, or you had a non-cluster index, so in many cases, SQL Server will just take a range lock. In this case, range lock will be minimum like a -infinity to 100. So we will not lock the rows that are greater than 100, right? So you can create a cluster index to manage the lock. So important point, right? And now I'm going to commit the transaction. As soon as I commit the transaction, and I go back and see my locks here, they're all gone, right? They have been released. You see that? So this is actually about all the isolation levels. If there's a question, please let me know. But this is pretty much what I wanted to explain to you. Now, I want to do one more example with you. Let's say I want to update a row, right? In this case, I'm saying update the row where C1 is equal to 1. So I'm going to do update. Now, if I look at my logs, when I do update, you will see that I got a intent exclusive lock on the table. I got exclusive lock on the row, which I'm updating. And I also got an intent lock on the page. So because row lives inside a page and page is part of the table, right? So two intent locks and a exclusive lock. Now, if I go to a second session, which is actually an interesting session, which I'm going to talk about, if I say select from basic locking C1 is equal to 20. Now, here's the interesting point. See here, the query that I gave was where C1 is equal to 1. So I'm looking at row with C1 is equal to 1. And here, I'm looking at a row that is C1 is equal to 20. All right, so I'm going to enable this execute plan. Actually, there's no reason for me to do it, because so what I'm going to do is I'm going to run this query. And notice this query is getting blocked. Okay. Notice this query is waiting. This guy is waiting. Now the question that you will ask is why? Because I'm accessing a different row. Why it is waiting, right? And the reason for that is because for this table currently there is no index, so it has to do a full table scan to find the row which matches the predicate that you have, which is C1 is equal to 20. So it has to go from page 1, it hits the first row where C1 is equal to 1, and that row is locked. So it cannot really see that row, so it has to wait till that lock is blocked, right? You see that point? Okay. Now let me do this. I'm gonna actually what I want to show you, I'm gonna stop this guy, right? I basically canceled my query. Now, if I want to run the same query, I'm going to change that to 20 here, right? If I do this guy, and I'm saying no lock. No lock is a hint, which is the same as read uncommitted, right? When I run this, I see that, because in this case, it did not take the lock. You see that point? Okay. Now, I want to show you one more thing. I'm going to run this query again. And in this case, I'm going to enable this actual execution plan. And this is something I want to show you, something that we have improved. So if I run this query, it's going to block because there is a row that is locked by the first transaction here, right? Now I'm going to commit this guy. So what I'm going to do, I'm going to commit on the first session here, and this query will run fine now, right? Now if I look at the execution plan and notice this is the table scan, right? I was talking about. Now if I look at the properties of my select statement, and notice this is something new, improved information about the execution plan. If I look at the wait stats, so what it told me is, you know what, when I was running this query, I was waiting for share lock. You see that? In this case, it says, I think it should have said I was waiting for the lock. But now with the plan, you can see why there was a blocking in the query, why the query was running slow. Because if you look at the query time stats, CPU time was 18 milliseconds, but elapsed time was much, much longer because there was some wait that was in the system, and you can look at the wait stats and it will tell you exactly what went wrong, right? Okay. Now to solve this kind of a problem, right? I'm gonna cancel this guy. Sorry, what happened here? Basic locking. I'm sorry. I need to run this query again. My apologies. I'm going to do an update again. Okay, I'm going to do C1 minus 2. Let me just see, there's no row here. Okay, I'm going to begin this transaction, right? So this guy is updating, and I'm going to run this query. Select C2, and you will notice it is waiting, right? And now I'm going to go and commit this guy, and this got unblocked. If I look at the query here, and I look at the properties and wait stats, and it is showing me here, notice it is waiting for this lock. So by looking at the queries, so for example, like you were running a query and somebody comes and tells you that that query was taking this long, right? If you had the execution plan on, you can easily find out the reason the query ran slow because it was waiting for this lock and it waited for this much time. Okay, it just makes the debugging that much easier. So now what I will do, I will create a non-clustered index on this table. Okay, I'm going to create a non-clustered index on C1. Okay. Sorry, I go here, I create the non-clustered index. All right. Now I'm going to run my transaction resolution level is still read committed because that's a default. I'm doing the same query. I'm going to update, right? I'm going to update. All right. And now if I go here and run this query after I have created a non-clustered index, right? Okay. So I'm going to go back to 20 again. I'm going to run this query and I have my actual execution plan on. Okay. When I run this guy, notice this ran fine. Remember when I did not have the non-clustered index, it blocked because it had to do a table scan. But now, because I have an index, it used the index to go to the right row. It did not have to look at the row that was C1 is equal to 1 because my predicate was C1 is equal to 20. So it went to the non-clustered index and found the row. So one of the rules for you to unblock your workload, if you have reader, writer blocking, to make sure that index paths are being used to access the data. When you have a table scan, chances are you will run into blocking issues. Okay, so I'm going to stop here on this demo. Go back to my slide. I don't have a whole lot of time, but let's just go one by one. These are all important. Now, the second thing I want to tell you about is the lock escalation. Now, imagine this. You are updating large number of rows. So, for example, I'm updating 1,000,000 rows. Now, as I told you before, to update 1,000,000 rows, we have to lock each of the rows, right? One row at a time. So that means we will acquire 1,000,000 locks. Now, acquiring a lock takes CPU instructions. Acquiring a lock takes memory in the SQL Server memory, right? It takes around 100 bytes to store the lock information. And once your update is done, you commit a transaction, those locks have to be released. So imagine this, you're acquiring 1,000,000 locks, right? Taking memory in the system, and once the transaction commits, it releases those locks, right? So it all adds to the CPU overhead in the system plus the memory, right? So this is how it is, right? Hobbit stands for heap or a binary tree. Pretty confusing acronym, but it has been like this for a long time. So notice yellow shows the pages. Yellow shows the pages and the rows, right? So I'm running a query, update 1,000,000 rows. So we will get all these locks that I'm showing you on the right side. Intent lock on the page, intent lock on the Hobbit, which is the table, and exclusive lock on the rows, right? This is going to be expensive. And the total memory will be 100 megabytes because each lock takes around 100 bytes. Okay? So this can be very inefficient. So what SQL Server does behind the scene, it escalates the lock because it says if I'm going to get more locks, why not escalate the lock at the table level, which will make me much more efficient. Now this escalation that we do, it is on a, if I can get escalation, then I'll do escalation. Otherwise, I will not. I will, after some time again, I will escalate. So that's the complex policy. And the reason is, right, if there is somebody else doing some changes in the table and you want to escalate, we will block. We cannot escalate. So you will continue to take locks like the way I'm taking here. But if there's nobody else, then we can escalate. So the rule is lock escalation. So if lock escalation succeeds, that's an important point. It does not have to succeed. Then we will release all these locks, and then take the lock at the table level. So that you can imagine is much more efficient. Now we trigger the lock escalation, and this is actually a confusing statement, but I'll try to make it as clear as possible. Within a statement, if number of locks acquired on a table, okay, I may have I have a SQL statement that is scanning 3 tables, and let's say the share locks, assuming I'm running under repeatable read, right? If number of those locks exceed 5,000, does not mean a thing. Each table 5,000 locks in a single statement. Okay, single statement each table. So if the number of locks on a single table exceeds 5,000, then we will attempt, SQL Server will attempt to escalate the lock. And if it escalates, then you're done. If it does not, it tries to re-escalate after new 1250. So from 5,000 and 6250, then another 1250 onwards, and so on. Okay. So the lock escalation is from row to table or a partition. We in fact allowed escalation at a partition level, assuming table was partitioned, starting I think 2008 R2 or 2008. I don't remember that, but that's what we do, right? This is what the escalation is. Now the challenge for escalation is, 5,000 is a very arbitrary number. Now, if for example a table had 10,000 rows, escalating at 5,000 makes sense. I mean, 5,000 may be too high a number, right? You want to escalate at a lower number. If you have 100,000 rows, you can say 5,000 makes sense. But if you have, say, 1 billion rows, if I update 5,000 rows, escalating at a table level doesn't make sense, because billion rows are a lot of rows, right? So we have heard customer feedback, and rightly so, that why don't you make a percentage? If I'm updating or deleting 2% of the rows or 5% of the rows, then escalate. Something like that, right? So that way you move away from absolute number like 5,000 and go to something more sensible like a percentage base, right? So what we found was that we did a lot of experiments. I mean, it is very easy for customers to use this escalation thing. If we do that, it will not work with every customer workload, because in some cases they may want escalation to be at 5%, some people want 8%, and things like that, right? So then we got the suggestion, hey, why don't you make it configurable, right? I will decide. Now the configurable thing was that we believe many customers will use the wrong configuration, because configuration will be at the database level or instance level, and things will get messy. So we decided that let's not do that, right? So what we provided to do, this is 2008, I think I was responsible for this work item. So now we allow you to say, for this table, do not escalate, or that means disable lock escalation. Or you can say my escalation is at a table level, that means I escalate from row to the table. Or if you choose auto, it can escalate to a table or to a partition level. So this is pretty much what we provide. Now let me show you a quick demo on the escalation. It's a very, very simple idea. So I'm gonna close this guy. Warwick, is there any questions for me so far, or things are okay?
Things are okay, Sunil.
Okay. All right. So I'm gonna go and show you a lock escalation thing. It's a very, very simple thing. Lock escalation. So here I will create a table, calling it T escalation table, because I'm going to test escalation. Okay. And now I'm going to create a cluster index on this table, and I'm going to insert 10,000 rows into this table. Okay. The reason I'm inserting 10,000 rows, because I wanted it to be more than 5,000, right? This is where the lock escalation will trigger. So what I'm going to do now is, these are the performance counters. I just want to show you the lock got escalated here. Okay, these are performance counters. So what I'm going to do, I'm updating all the rows in my transaction. You see that? Update the escalation set C2 to C2 plus 1. So I have 10,000 rows. I'm going to update all the rows. So I expect in this situation, lock escalation will happen, right? So it will run this. I do this. And notice it said lock was escalated, which you expect, right? So this thing happens behind the scene in the background. You can't change it, right? Of course, I can use alter table command to say don't escalate the lock, and then lock escalation will not happen. So the question is, what should you do? So if you have a table that is accessed in a very highly concurrent way, right? You know that escalation can cause blocking, right? Because escalation happened and it is being accessed by a lot of transactions, they will get blocked, right? So for that table, you should say, I'm not going to escalate the lock. You see what I'm saying? So you say, disable the escalation. So that's the strategy that we provide. I'm not going to show you the demo where I can say disable the lock escalation and the escalation will not happen, but that's a very simple thing to show, right? Okay. Now the third thing that I want to show you, which is also very, very interesting and often not as clear. So everybody, I think I would imagine that even if you have not heard about isolation levels or whatever, everybody knows that there's a locking in the system where you lock a row or a page, right? At least that. Now, something that is not so obvious is the latch, the page latch. Now, what is a page latch? So when you have a row, when you have a table in SQL Server, and that is true, that was true with Sybase, that was true with Oracle, everybody has the same thing. There's a latch. Now, what is a latch? Latch is a short duration lock. Okay, when I say short duration, it is not transactional. It is short duration. It is taken for a very short duration for the time it is needed, and then it is removed. That's a page latch. And why do we need it? Imagine this. You have a page, right? I'm showing you by red the page header, and there's a row which is shown in brown color. Okay, and there's a free offset here. Now imagine I want to insert another row on this page. Okay, I want to insert R2. So I need to figure out where do I insert. Obviously, I cannot insert the row on top of R1. I have to start the row R2 from where R1 has finished, right? So I'm going to insert the row R2 after R1, right? Now there could be gaps. It's a very complex way to manage, but the point is we need to make a physical change to the page, right? Once I do that, I change the offset to the new offset. Now, if I may insert the row R2, I may not have committed the transaction, so I'm still going holding a exclusive lock or R2, right? You will agree, because I cannot release the lock until my transaction commits. However, this page can have another row R3 from my different transaction, right? So what happens is if multiple transactions are inserting row into the same page, we need to allow only one transaction at a time, because if you allow both transactions and they look at the free space offset after R2, they will write their row 3 and row 4 at the same free offset, right? You agree? And you don't want that, because then data will be overwritten. So to ensure the physical consistency of the data on a page, SQL Server takes a latch. Latch means exclusive access. So if I want to insert a row in transaction R3, I'll take an exclusive latch on the page, copy my bytes. Once my copy is done, I will release the latch so that somebody else can come and insert another row if they want, right? So that's the latch. And there are two kinds of locking modes. One is the exclusive latch. That means nobody else can insert. And there is a shared latch. Shared latch means if I'm reading a row from a page, I need to take a shared latch so I can copy the bytes. And the good thing about shared latch is that multiple transactions can read from the same page without blocking on each other, because it's a shared latch. Nobody's changing the data. But if suppose somebody wants to insert a row, they need to get an exclusive latch, and that will get blocked, right? Okay. So this is the latch. Now, what is the problem with the latch? The problem with the latch is if you have very high concurrent activity in your table, you can see a lot of latch waits. And I'm going to show you through a demo. So for example, this is the common problem, right? If you have identity column in a table, and that's a cluster index, I've seen that many customers are doing that. Now everybody inserting the row, since it is an increasing value, everybody gets stuck on the last page, everybody inserting row to the last page. And that means everybody's going to get blocked on the latch. You will see a lot of latching. You can also see a lot of latching if you have a small table that is very hot. Everybody's updating rows in that small table. Chances are they will step on each other onto the same page. You will see this kind of problem. You will see latching in many other structures like GAM structures and so on and so forth. But I think let's not worry about that. I'm just going to talk about in the context of a table. So that's the latch. So what can you do? What can you do? What you can do is you can cluster on a different column. Now, this is easier said in a presentation than done in an application environment. You cannot really change clustering that easily, right? So you can try different things. For example, you can say, I'm going to create a cluster index on this table, and I'm gonna distribute rows, fewer rows across multiple pages. So for example, if I had a small table, I may choose in such a way that there is only one row per page, so I can minimize latch contention. There are some tricks you can do, right? You can partition the table, right? You can partition the table. That means each partition will have its own last page in the cluster index scenario, so you can do something there. Or you can add another major key column. But the point is, there are very limited things that you can do to remove the latch contention, and that is something that you have to deal with, especially when the latch is on a data page. SQL Server has latching on many other structures. For example, I was talking about the SGAM structures, internal structures. Like a user fixing their tables, SQL Server has the same issue when the concurrency goes beyond a certain limit. How do I minimize the latching, blocking? And I think we, in fact, keep scaling our internal structures that are also protected through the latch, right? But let's not worry, but this is a common issue. So what you can do now with 2014 onwards, in many cases, you can remove latching completely by moving to memory optimized table. And last resort, which is not really a resort, I mean, you can't change the application, right? You're working on an application. Now let me show you a quick demo on the latch. And I know we have only 8 minutes left, so I'm gonna be focusing on that quickly. And I go here, and I want to show you the latch contention, okay? So here, what I have is I'm going to use my same database, log test database. And notice I enabled this database with memory optimized table. I added a memory optimized file group. I added a file. So now my database is enabled for memory optimized table. And interestingly, some of you may not know that starting 2016 SP1, memory optimized tables can be created on a standard on lower edition, so you don't have to buy enterprise license to use memory optimized tables. Very, very powerful. Same thing stands for column store as well. Okay, so for now, before this talk, I had created the memory optimized database. So I'm going to create this table T latch, right? I'm going to drop the table, and I'm going to create the table. Now, when I did a cheating here, I have only 2 columns. Both are integer, so around 8 bytes, right? So row length should be around 11, 12 bytes based on the metadata. And now what I'm doing is I'm going to insert 100 rows into the table, right? 100 rows. Done. Now, because it's such a small table, each row is 8 bytes, and the page size in SQL Server is around 8,000 bytes, right? 8K, so 8,060 total size. So all 100 rows will be on the same page. I wanted that because it's a small table. And now what I'm going to do is I have a stored procedure where I'm updating the rows. Okay, I'm updating the row multiple times. So here I'm updating the same row that you can see here, like in a loop. I'm updating the same row 100 times. This is my stored procedure. Okay, now what I'm going to do is I'm going to run this stored procedure in a tricky way. So I'm going to do the clear the wait stats. Clear the wait stats. Now I go to my command window, and I'm going to run this command ostress that you see here. Ostress. Let me see if I can make it bigger. Sorry. Okay, this is not working. But you can read it that it is saying ostress here. Ostress. N20 means I want to run 20 concurrent sessions. Okay. Each session will run this stored procedure that I have, update data disk base. I'm updating table. Remember, in the loop 100 times each, I'm going to run this stored procedure 20 times. So I will kick off 20 threads, 20 sessions, and each session will execute this stored procedure 20 times. So that means each procedure updates 100 times, right? So 20 times into 100 is 2,000. So each row is getting updated 2,000 times, right? 2,000 times, and I'm running 20 concurrent sessions. Okay, let me run that. Okay, it's going to take 3-4 seconds. So it's done. Like it finished in 2 minutes 46 seconds, right? And I want to show you there was a latch contention. And I come here, and if I run this command, you will see the latch contention, exclusive latch contention, which happened because I was I was inserting the rows, updating the rows on the same page, and there is also a shared latch because before you update, we need to read the row, right? Okay. So notice the total wait time was around 22 seconds, it says, right? Because I'm running multi-threaded. So this is like a whole serious amount of waiting that I did for my latch contention. Okay. Now this can eat up a lot of blocking, can eat up a lot of query performance, and something to be aware of. So now what I did was I go back to my latch contention and I change my table to memory optimized. I changed my table to memory optimized. And same schema, right? Two tables, two columns, C1 and C2. And then I also inserted 100 rows into this table, just like before. There are in this table. And then I can show you the select star from this table so that you know it's like 100 rows. And then I have a stored procedure which is doing the same thing that we did before. I'm updating 100 rows just like here, 100 rows. But since memory optimized tables do not have a latch contention, I will not see any latch contention. So I'm going to run this guy here. I go, remember this took 2 minutes and 46 seconds. And here I'm updating, notice I changed my command, update data in memory based. Okay, I'm going to run this command. And notice it finished in 358 milliseconds. Now you will see a couple of transactions got aborted, but don't worry about that part because in memory has a, if I had to run this demo in a rather clean way, I need to make sure that concurrent sessions do not update the same row. In a transactional workload, that doesn't happen commonly. So for now, let's ignore. But the key point is that my queries ran that much faster because I removed the latch contention for sure. Of course, they speed up because of in memory as well, but latch contention also contributes to that, right? Okay. So I'm going to stop here and go to my slide. Now the last thing that I want to talk about before I go there, can I do 10 more minutes or is a hard stop in 3 minutes?
No, we can go for a little bit longer, Sunil.
Okay, so just allow me to do this one and promise to stop after that. Now the reader-writer blocking. Remember I was talking about Oracle, where Oracle read committed is not blocking. Okay. Now here is the example I want to show you. Let's say I have a page which I'm showing you in a gray color, which has a red row called row 1. Now you want to update this row, so you have start a transaction, and when you start a transaction, you want to update the row. You update the row blue, right? From red it became blue. So when you change the row, you need to get exclusive lock on that row, right? Because otherwise everybody can read the data, dirty data, right? So let's say I change the row from red to blue, but I have not committed my transaction. Now here, a transaction that is trying to do select on this row, what happens? It wants to get a shared lock on that row because it is running under read committed. Read committed makes sure that I want to see the transactionally committed data. Blue at this time is not transactionally committed, right? Because the transaction 1 has not yet committed. So it will get blocked, right? And then transaction 1 goes away, and now transaction 2 can read the blue row. You agree? This is how it works. Now, it is possible for many queries, I think most queries that I know, they would be fine reading the red row. Okay, so the point I'm making is here, notice the row was red. That means that red row was committed row, right? Nobody had, I mean, this is before transaction 1 began, the row was red. It was committed, right? Okay. Now transaction 1 made it blue. Now the reader that is coming to read the row 1, reader row 1 would have been fine to see the red value, but not the blue value because transaction 1 has not committed. It would have been fine to see the red value, right? Because that was transactionally committed data. So this is the most important point. So what we allow now with the 2005 onwards, you can tell SQL Server that my reader, in this case transaction 2, is okay to read the row that was red. That was before it was changed. Okay. And the way we implement this thing is by row versioning. So what we do is, when the row was being updated by transaction from red to blue, what we do is we copy the red row somewhere else, and on the page it shows to be the blue row. Now if the transaction 2 comes, it finds out, well, blue row is from a transaction that has not yet committed, right? So there's a page chain that figures out, or the row chain, which will figure out what is the previous value of the row, which is red. It will just read the red value, right? So in this case, that means transaction 2 was not getting blocked, right? Because it went and read the older version of the row. Now this is something that you can make enable in your database using something we call read committed snapshot, and I'm going to show you that example. Now this is exactly what Oracle provides. Oracle, when the current row is blocked, it returns the previous version of the row. Okay, the way I'm describing it, it is in a very simplified way. I mean, there are a bit more complexity on this one, but you get the idea that we use row version, which is row versions are committed rows, right? So we will just go back to the version chain and get the committed row. So that's what we do. Now this is important because if you use row versioning based read committed, then any blocking that you have between readers and writers is completely gone, right? Very, very powerful. So we provide two flavors. One is called snapshot isolation, and the second one is called read committed snapshot. I'm going to talk about that. Right, we just talked about that it is going to improve the concurrency of your application, so we recommend it very, very highly. So what we find is many customers are saying, I'm getting a lot of blocking, and in many cases you have a lot of blocking, your CPU is running at 20% because everything is getting blocked. And what we tell customers, try RCSI, like read committed snapshot on your database, and suddenly they see the blocking is gone and their CPU can go to 50 to 60, whatever higher number, they get better throughput. Very important point, okay? So here is the thing about RCSI. So there are two ways SQL Server allows row versioning to be used. One is at the statement level, and second one is at the transaction level. So I'm going to talk about at the statement level first. So you can enable this thing at the database level. You can say allow read committed snapshot at the database level, okay? You can do that. Now when you do that, writers do not block readers, because writer took an exclusive lock, but reader will go to the previous version of the row. Readers do not block writers because a reader will not take a shared lock. It just reads the row version. Writer comes, it will copy the row that was being read to the version chain, and you're fine, right? There's no blocking. But writers will block writers, right? That is not stop. It makes sense, right? Two people cannot be updating the same row, right? We have to protect that, right? That makes sense. Now, so it can block, it can reduce blocking between readers and writers, and in many cases can reduce the deadlock. Okay, so here's the example. I create a table T1, and I have two columns, C1 and C2, and I insert a value 1, 5. So this table has only one row. Now I start on a transaction 1, and it says transaction 1 here, update T1, set C2 is equal to 9, where C1 is equal to 5. So then that means the red row was for me 1, 5, right? This is the red row, and 1, 9 is the blue row, right? Because I changed that in the transaction. I'm trying to correlate with the picture that I had before. Now if I run under RCSI, what happens is, if I run the query, I say select C2 from T1, it will return 5, because that was the value of C2 before it was updated to 9. It will return 9. Now once your transaction 1 commits, when the transaction 1 commits, if I run the same query again, I will get 9, right? Because once the transaction committed and I run the same query again, now the new committed version is the red version, not the blue version. I got confused there. Original one was red, and then it was changed to blue. So now I can get blue. So this is the RCSI, read committed snapshot, that is at the statement level. Now I'm going to show the same thing under snapshot isolation, okay? So I'm just going to go to the next slide, which is snapshot isolation. Snapshot isolation gives the same behavior, but at a transaction level. And I'm going to show you an example on this one so it becomes clear. So same table, T1, C1 is equal to 2 columns, and I'm going to insert 1, 5. So here I'm inserting a row. I inserted the row. I'm updating the row saying update T1, set C2 to 9, where C1 is equal to 1, right? That means now my blue row now is 9 for C2, and my red row was 1, 5. Now if I run under snapshot isolation, right? I'm running under snapshot isolation, begin transaction. Now what happens is the snapshot isolation transaction says what is the state of my database at the beginning of my transaction. Okay, so the state at the beginning of the transaction was, the committed state was 1, 5. All the transactions that had committed, it does not, snapshot isolation says I don't worry about anything that is ongoing in terms of transaction. I want to see all the committed values that were there at the beginning of my transaction. So when I do the query C2 from T1 where C1 is equal to 1, it will see 1, 5, right? It will get 5, right? Because that was a committed state of my row. Now, if I commit my transaction 1, right? So now the blue row is 1, 9, right? That is committed. But if I run the same query under transaction snapshot isolation, guess what it will return? It will return 5, because at the beginning of the transaction, the state was red for this row. Blue was not there. Blue happened while I was executing this transaction, right? But now if I commit the transaction and I run the same query again, that is a new transaction, now it will see the 9. So the difference that you see is it is under snapshot isolation at the statement, at the transaction level, and the RCSI at the statement level. Okay. So again, this is something that we recommend our customers to use RCSI at the database level, because that's the most common scenario to remove reader writer blocking. Okay. So I think I will show you finally the isolation level table, and then I'm going to conclude my presentation. So essentially what you have is, remember I was talking about isolation level, read commit, uncommitted, right? All these things are there, right? Dirty read, non-repeatable read, phantoms, etc. But read committed now, there are 2 versions. Locking version, which is based on locks, and second one is based on the row versioning. It is optimistic locking. All right. And the repeatable read is here, and the snapshot isolation sits between repeatable read and serializable. So this is pretty much what the isolation level looks like in 2005 onwards. Okay. The most common isolation level thing that I've seen is the read committed snapshot isolation level, where you enable the row versioning at the database level. So that's something we recommend very highly. That is, if you are running into locking blocking issues, think about enabling that. Okay, with that, I think I'm going to conclude this presentation. Let me just go to my summary slide. So in this presentation, we talked about concurrency models, starting with isolation levels. We talked about log escalation. I did not talk about granularity, log granularity in detail, but log granularity means row, page, table, partition, and but you get the idea. We talked about page latches. We talked about row versioning based isolation levels. Unfortunately, I could not cover deadlock, but that's where it is. So I'm hoping that this will give you some basic idea about locking and the strategies that you can do. For example, index, right? What you could do about log escalation, because log escalation can cause a lot of blocking. You can prevent that. I talked about page latching, and I also talked about row-based versioning to remove blocking between readers and writers. With that, I think I've concluded my presentation. Thank you for joining. And if there are questions, I'll be more than happy to take those questions.
Thank you, Sunil. Do have a question for you. So we're undertaking some DML operations, and we're receiving a lot of exclusive and shared locks on the table. We're undertaking 1 million rows, a 1 million row update. How can we reduce the blocking that is occurring for all other statements?
Right. So So first of all, there is no fixed answer to this one. So the first thing to notice is the update that is updating million rows. You need to look at the query plan to see, is it uh, taking a lock at the table level? Is the lock escalated? Because lock could have gotten escalated. And I showed you the script which you will be able to download. So if it is because of escalation, you can set escalation, disable escalation, so this will not happen. Right? That is one important point. And notice the guys that are getting blocked, the queries, what is the query plan? Are they doing a table scan or they are going through the index? So if you figure those things out, you will be able to get higher concurrency. Now, if the other transactions are either want to read the rows that are being updated, they can be fixed through RCSI, right? Read committed snapshot. But if those guys were updating the rows that you are also updating, they need to block, right? So there are a few things that you can do. So my suggestion is look at lock escalation, look if you can use RCSI, and look at the query plan of the other guys, whether they're using indexes or not.
Thank you. I've got another question.
Sure.
I read that using RCSI uses tempdb. Can
That's
you
right.
please tell what we need to watch and how to tune tempdb?
That's right. So it's a great question, and in fact, I've done a whole big blog on this one. You are absolutely right that a row version, number one, row version is kept in tempdb. Okay. Now that version needs to be kept as long as it is useful. So remember, I was talking about a red row and a blue row. So the version is red row, right? Because the transaction that updated the red row to blue, the red version needs to be kept around as long as there are transactions that are active before blue row was committed, right? Because once the blue row gets committed, then nobody needs a red row, right? They can read the blue row now. So think about this, right? If I have a transaction that was active, and now this transaction, update transaction, converted the row from red to blue, the transaction that was active has to read the red row. We cannot remove the red row. Even if you commit the transaction that changed it to blue, red row has to be kept. But all new transactions will get the blue row. So in general, that causes tempdb to grow if you have a long-running transaction, right? If I say begin transaction and read the red row, and then you go home for a long time, the transaction is active, the version cannot be cleaned up, right? So there could be a buildup. But in general, what we have seen in a transactional system where a number of transactions are short duration transactions, the tempdb does not grow that significantly. We do provide a lot of telemetry in terms of the storage taken by version stored. In fact, we have improved some diagnostics in 2016 SP1, if I'm not wrong, with some CU. I can send you information. So yeah, so you need to monitor it. But the point is, unless you have long-running transactions, you should not see this kind of a buildup. Now, there's a formula that we have created, which is, I think I can describe it just what it is. Essentially, the longest running transaction that you have in the system in terms of time and the transaction throughput, and you multiply that by 2, and it will give you some number and say this is the extra space that you need in tempdb for version store. It's hard to describe verbally, but I think, as I said, there's a blog on this one. So your point is absolutely right on. You need to watch out for provisioning the tempdb appropriately for the version store.
Thank you, Sunil.
Yeah, good.
Well, if there's no more questions, I'd like to say thank you to everybody for coming along and being part of this month's session. I'd like to thank Sunil for giving us a fantastic session on concurrency in SQL Server. So with that, we come to the end of, we've just got, thank you, Sunil, for sharing your knowledge. You greatly accelerated my understanding of these concepts.
Okay, one thing I'll do, like the blogs on the tempdb/row version, everything, I'm going to send you all the information hopefully in a day, and you can share with everybody. I think it'll be useful. And thank you for joining again. Take care.
Excellent. Thank you, everybody.